Hello, thanks for tuning in. My name is Pat, and here I'm going to discuss a connection between the square root function and the geometric series. Our assessment of this connection will generate a rational sequence where each sequence term approximates the square root function with successively increasing accuracy. Some similar square root computation methods include the Babylonian estimate, Pell's equation, the Lucas sequence, and Goldschmidt's algorithm. Description of these and other methods are linked in the description. Utility will be made of fractional exponent interpretation of roots. A list of prerequisite topics utilized in this footage include elementary algebra, exponent properties, summation notation here defined at the top of the board, geometric series, limits, and sequences. A self-contained online resource to review these topics is Paul's Online Math Notes, linked in the description with several other sites and sources both on and offline. The square root of a finite, non-square, positive real number is never a fraction of two whole numbers. In a situation where someone is looking to approximate an irrational square root with a sequence of rational fractions, a useful place to begin might be to rationalize the square root denominator and substitute the outcome into the algebraic formula for the geometric series. Taking the definition of the square root of u, where u equals the square root of u times itself, dividing both sides by the square root of u rationalizes the square root of u. Next, using the additive identity property of algebra allows addition of a parameter we can call epsilon into the denominator of rationalized square root u. This process leads to a form of rationalized square root u directly comparable to the algebraic formula for the geometric series, here labeled S. With the square root of u equaling u divided by the square root of u equaling u over epsilon times the quantity 1 over the quantity 1 minus x for all x equaling 1 minus the square root of u divided by epsilon, where 1 over x equaling s equals the limit as n approaches infinity of the nth partial sum of the geometric series if the absolute value of x is less than 1. From algebra, the geometric series nth partial sum formula follows from comparison to the result of factoring an x from every term after 1. This change relates the sum to a form in terms of itself. Subtracting x times the nth partial sum from both sides and factoring the nth partial sum from the left-hand side yields the desired result after division by the quantity 1 minus x. And with the absolute value of x less than 1, implying that 0 equals the limit as n approaches infinity of x to the power of n, it can be shown that the geometric series formula is S equaling the limit as n approaches infinity of the nth partial sums equals 1 over 1 minus x. The modifications made to rationalized square root u apply to immediate comparison with the geometric series formula after a substitution x equals 1 minus the square root of u over epsilon into s equals 1 over quantity 1 minus x. This produces an identity. Square root of u equals u times s over epsilon. Since convergence of s equals 1 over quantity 1 minus x is only possible if the absolute value of x is less than 1 for all x equaling 1 minus the square root of u over epsilon, these conditions imply two convergence criteria: u greater than 0 from 1 minus square root of u over epsilon less than 1, and u less than 4 epsilon squared from 1 minus the square root of u over epsilon is greater than negative 1. With convergence criteria verified, the intended and central result is reached by utilizing the definition of an asymptotic relationship, a tool for conditional approximation where the limit as n approaches n naught of f of n over g of n equaling 1 mutually implies that f of n is asymptotic to g of n. This limit, defining an asymptotic relationship, is the principal stage for formation of our approximation to the square root of u. Approximation generator assembly occurs from applying this limit definition of asymptotic relationships to the combination of geometric series partial sum formula and the now established identity square root of u equals u times s over epsilon, forming this approximation generator. The primary result is reached from a comparison of the two identities g of capital N equals the square root of u equals the limit as capital N approaches infinity of u times s subscript capital N over epsilon, and f of capital N equals u times s sub capital N over epsilon with the asymptotic relation definition limit for f of capital N asymptotic to g of capital N, such that 1 equals the limit as capital N approaches infinity of u times s sub capital N over epsilon times the square root of u equals the limit as capital N approaches infinity of f of capital N over g of capital N. This achieves the goal of an approximation with an asymptotic relationship between the square root of u and a geometric series here labeled capital A subscript capital N. This asymptotic relation serves as a generator for this particular sequence of rational estimations to the square root function of u. This generator will be abbreviated RAG, short for Rational Approximation Generator. Direct asymptotic estimates square root of u asymptotic to lowercase a subscript capital N are formed by solving for the square root of u from n terms of this resulted RAG asymptotic relation. This direct estimate process begins with a simple initial approximation square root of u asymptotic to u over epsilon equal to lowercase a subscript 0. Further estimations are found from the initial estimation by using the recursive nature of the geometric series nth partial sum definition, labeled here at the bottom of the board. Proceeding with recursion for capital N equals 1 requires application of the simple first-order expansion of this sum from lowercase n equals 0 up to 1 of the quantity 1 minus the square root of u over epsilon and quantity to the power of lowercase n equals 2 minus the square root of u over epsilon. The resulting approximate linear equation in first-order terms of the square root of u, when this sum is substituted into capital A subscript 1, this first-order equation in terms of square root of u is fairly straightforward to solve for the approximation lowercase a subscript 1, and that is done by the following. That is that you set capital A subscript 1 equal to 2u over epsilon minus u times the square root of u over epsilon squared asymptotic to the square root of u. And then we find that adding u times the square root of u over epsilon squared to both sides yields 2u over epsilon asymptotic to quantity u over epsilon squared plus 1 and quantity times the square root of u, which is further equal to the quantity u plus epsilon squared over epsilon squared quantity times the square root of u, so that when you multiply by epsilon squared on both sides and divide by u plus epsilon squared, you arrive at lowercase a subscript 1 equal to 2 epsilon u divided by epsilon squared plus u, which would be asymptotic to the square root of u from the following or the previous algebraic manipulations. This result, the formula lowercase a subscript 1 equal to 2 epsilon u over epsilon squared plus u, can be called the first order approximation to the square root of u. In this video, I won't have time to detail the higher order approximations that are derived by this modified common ratio geometric series, but in the next video I will cover higher order approximations and the relationships between them and some other results that occur when you generalize the order of approximation. But I wanted to take a moment and review the Babylonian estimate and the recursion that is used in that to demonstrate that this method for approximation, which relies on the geometric series, that it is on track in its results. And so, quickly overviewing the method that is prescribed by the geometric series relationship, that asymptotic relationship that we arrived at from utilizing the algebraic formula for the geometric series after rationalizing and modifying the denominator of the square root function of u. Well, we have arrived at two asymptotic relationships. Actually, there's the first one arrived at capital A subscript n asymptotic to the square root of u, where the capital A subscript square root, where the capital A subscript capital N identity is u over epsilon times the sum from lowercase n equals 0 to capital N of the quantity 1 minus square root of u over epsilon to the power of n. That is asymptotic to the square root of u. Solving this, evaluating the sum for a particular value of capital N, and simplifying it, you'll find it's always linear with respect to the square root of u, and then solving that asymptotic relationship for the square root of u gives you the second asymptotic relationship, that is lowercase a subscript capital N asymptotic to the square root of u. These are the direct approximations. These give you the precise and particular numerical estimation for a given value of n or a given order of accuracy. And so we find, evaluating this capital A subscript n subscript capital N asymptotic to the square root of u, we find that evaluating this out to the 0th and 1st values, we find u over epsilon and 2 epsilon u divided by quantity epsilon squared plus u as the first two asymptotic approximations to the square root of u. And you also can see that because u divided by the square root of u equals the square root of u, that therefore the square root of u would be asymptotic, and the square root of u would therefore be approximate to u divided by a0 and u divided by a1. Now, that's where the Babylonian estimate comes into comparison, is with respect to u over a1. You see, the Babylonian estimate begins when you say that you want some number, some guess, asymptotic to your square root function. A good idea of what that guess could be is that the square of your guess should be roughly equal to or asymptotic or otherwise approximate. The square of your guess should be approximating of the value you're taking the square root of. So your guess, epsilon, if your guess is epsilon, then the square of your guess has to be asymptotic, or has to be approximate to u, where epsilon is approximate to the square root of u. And now you see also, though, that u divided by this initial Babylonian approximation, u divided by that approximation gives you another approximation, u over epsilon, because u over the square root of u equals the square root of u. Because of that, you would find that u over b0 would be asymptotic to u over the square root of u, which would be asymptotic to, or equivalent to the square root of u. The Babylonian recursion, the estimation reproduction system, comes from taking the average of this rationalized approximation, this rationalization of the first approximation with the first approximation. So you take the first approximation, your first guess, epsilon, and you take the average of that first guess with the rationalized form of that guess. So you take the n plus first Babylonian approximation of the square root is equal to the square of the nth Babylonian approximation plus u, the number being square rooted, and then you divide that quantity by 2 times that nth Babylonian approximation. And you find, applying that to the 0th to find the first, you find that the first Babylonian approximation, the first order Babylonian square root approximation equals u squared over epsilon squared quantity plus u divided by the quantity 2 times u over epsilon, which simplifies to u plus epsilon squared quantity divided by 2 epsilon, which equals u divided by this lowercase a subscript 1, which is our geometric series derived approximation, first order approximation to the square root function. And so that demonstrates right there that the Babylonian estimate is consistent, or rather this geometric series estimation of the square root function is consistent with the Babylonian estimate. And so with that, I'd like to conclude this assessment of this approximation. I will be producing other videos, hopefully 1 or 2, that further detail the properties of this estimation, and I will talk to you then. Until then, take care.